Greetings, healthcare colleagues. My name is Kevin Krawczyk. I'm the founder CEO of Chemical Q Device, here for discussion 84. This is Thursday, May 25th, 2023, quantum machine learning in medical innovation. Now, I put up on the slide, that cover slide, Google. So Google is known for recently, as more people file in here, bigger quantum computer than a smaller computer, but less error than the smaller quantum computer with that. Also for quantum supremacy back in 2019, doing stuff with quantum sensing since that time. AWS, so this is that top middle one, is basically you have their high performance simulators. So DM1, TN1, SV1. You also have a number of manufacturers. They have a second IonQ on AWS Braket now. So Braket is their quantum computing service. And you also have OQC, QEra, Rigetti, and Xanadu in varying amount of costs per to take shots in those instruments. And then IBM, most recently 100,000 qubits in 2033, they say, the first quantum computer in healthcare. This is this year in 2023 at Cleveland Clinic. And also you can use Qiskit for free, in many of these cases. So IonQ, the second row that I included is basically, they say next year, first half of 2024, manufacturing facility. They're big in literature applications, meaning that of all these technologies, gate-based superconducting qubit, ion trap, neutral atom, silicon spin, you're typically seeing that ion trap technology with that. So in addition, Caltech, I would say they're one of the leaders universities-wise. John Preskill, the late Richard Feynman. They also have, basically this AWS partnership, and they have this hub, basically for quantum computing as well. And then you have MIT with Torch Quantum. You have quantum engineering. They're Peter Shor, Seth Lloyd, the HHL algorithm. The list goes on and on. MIT is big into quantum. And you also have Quantinuum recently, 32 qubits, the GHZ. So this is a maximally entangled 32 qubit, circuit. They have Ticket, and again, more literature citations. It's ion trap technology with that as well. And then Microsoft topological qubits, Majorana, Fermions, they just got DARPA 5-year funding. You can get free credits through it. So maybe between IBM Qiskit and Microsoft Azure, one of the two that offers, making it easier to get started. You also have Xanadu with PennyLane. So this is quantum supremacy they had back, the middle of last year. So they have a number of simulators, either Python-based, which are default.qubit, or you have C++, which is lightning.gpu or lightning.qpu with that as well. So I wanted to open up, definitely, so these are 12, and then kind of focus in on the first two as far as Google and AWS. Any questions regarding that, or, kind of news that you've read, or some developments? And you should be able to, so you can unmute and you can come on as well. And, I see a number of people returning here too. So feel free to, on these first two. So this is Google and AWS as people come on here.
I have a question, and thanks again, Kevin, for hosting these series. So I'm interested in the environmental impact of comparing these computational systems, compared to the data center that's loaded up with the, power-intensive GPU. So I see that the friction point for quantum computers, except for maybe IonQ, is the cooling mechanism that, that has to cool the quantum computer itself. I've seen for the Sycamore processor at Google that it uses a very minimum amount of wattage actually to drive the processor. It's just that it's not clear to me exactly like what the environmental impact is given, the cooling requirements of these systems.
Yeah, I mean, and I would frame this as basically, so IonQ does quarterly reports, and basically their qubit counts, you're not looking at too much. And then we heard the IBM news, 100K, especially, 10 years from now. Now, in theory, quantum computers are a lot more energy efficient than GPUs and CPUs. However, the error or the faultiness to it, especially in something sensitive field like finance or healthcare, will be a serious concern moving forward. So there's been efforts, say, for instance, to try to get the best out of, so you have a quantum computer, this is NVIDIA, they call it DGX, and then they're using a GPU to trying to fix that error. So you're absolutely correct. Like on a watt per basis with this, gate-based superconducting qubits like IBM and Google and Rigetti will require significant, cooling compared to the other technologies like ion trap. Silicon spin's not nearly as cold. It's a 1 Kelvin instead of millikelvin. Neutral atom, I don't believe requires much cooling at all. So, it's just what's the first one that's going to work the best kind of thing, right? Because, it's bidirectional. It shouldn't take up nearly amount of the footprint if we had a fully functional quantum computer with it. So that'll be interesting. Quantinuum, which is ion trap, they just demoed this 32 GHz circuit, and then it was taking up a small room. And that ion trap takes a less cooling, say, than the gate-based superconducting qubit. So on the side of gate-based superconducting qubit is there's been pushes to secure liquid helium, from the federal government. And I think that's okay, right? But the biggest issue, besides just, we need to pay the cost to cool it down, is it just has too much error relative to a quantum simulator or ion trap hardware. And you could probably find, material out there if you want to look at, say, for instance, like the energy efficiency versus a supercomputer for this specific task, because there's still things the supercomputer could do, CPU, GPU, that a QPU can't. So it's trying to offload it into the things that make sense to run on a real quantum computer.
Thank you. Yep.
Yeah. So, a lot of these things are in theory. So there's been a couple of articles out there recently. I mentioned Tom's Hardware. They said, plan on, GPUs, in the near term, GPU quantum simulators, which is quantum mechanics on a GPU, being the thing in the near term. And then there was a more recent, it's AZO, I think it was AZO 2Q or something like that. It's a market report, and they say prepare for rapid growth acceleration for quantum simulators, right? Because the IBM news this Sunday wasn't too hot for us, because we already were kind of thinking 1 million qubits by the end of this decade. It was kind of thrown out there. So now it's 100K, and then we have, potential quantum simulators like a GPU-based quantum simulator that can go to hundreds, if not thousands, of qubits in theory. This is NVIDIA. So anything else? So Google or AWS? So AWS is pretty much you're paying for it, but you get what you're paying for. Their simulators are quite good. The TN one, which is Tensor Network, can go up to 50 quantum bits or qubits with that. And, the other two, maybe more mainstream, DM stands for density matrix, SV1 state vector. So, and on the Google side there too, because I know there's people out there that are huge into Google. So Google is the whole Colab, Google Circ, QSIM. There's a fair amount that's gone into TensorFlow Quantum in incorporating a better quantum simulator to make your quantum circuits run faster. Speed is the big thing, right? So speed with quantum simulators tends to be the challenge now. I just ran a bunch, and it's 7 times slower than your average CPU approach that's GPU assisted versus using a quantum simulator. So yeah, anything else, Google or AWS? If not, we'll move on to IBM and IonQ. So most people ask, how do you get started in quantum computing? And I know there's at least one person in this room that has recently done stuff with IBM's tutorials, is basically start off with IBM Qiskit. It's free. It's spelled Qiskit. And then you can go through tutorials. You can try to better their scores that they got for accuracy or loss. It's free quantum computers to test on, up to 7 qubits or 10 qubits. But it's simple. Just run your own quantum circuit, and you just ran on a quantum computer. So the huge news, I mean, especially for this startup, is they were the first to put a real quantum computer in Cleveland Clinic, like front and center. Everybody can walk by kind of thing with Windows. And I'm sure it will be upgradable. The core components of it, less error and more qubits kind of stuff. But that's the news coming from IBM for sure. And anything else on IBM? Anybody else want to share? So it's easy. I mean, it's relatively easy. If you're coming from no coding background, you will have to get used to that. But, once you get going on it, it gets easier. Go ahead, Ron.
Yeah, how do I sound? I'm on a different computer today.
Yeah, it's fine.
Yeah, I finished the IBM 2023 Quantum Cat Challenge. I got all the way through the end of Lab 5. I'm actually pretty proud of myself, considering that at least half of the people who joined that challenge were PhDs. So it was fun and frustrating, and I had to get a little help, and I gave a bunch of help to other people. So it was really quite a interesting adventure. Also, at the very end, I was able to submit a job to their 127-bit qubit Eagle processor, but by the time I got to that point, the queue was so bad I had to wait so long. I was only able to submit one job, and it came back pretty much a mess. So the issue with the 127 qubit processor is you've got to send it a good circuit, and there's no way to simulate it. So that's going to be an issue moving forward. So, but it was a lot of fun. They've opened their IBM's opened their 2023 summer school. I missed the deadline for that as far as the advanced tickets, but they said there are going to be more. So I'm on their alert system to make sure I know when those come up, because apparently they had 5,000 advanced tickets and they sold out within a day. And that the summer school is supposedly free. I think the general admission is supposed to be free too, but I won't know that for a couple of days. And some other news is I'm going to be doing the Womanarium summer school. So yeah, my plates are going to be full. And again, the quantum computing stuff has been really fun. It's been challenging. You do have to change your mindset on building algorithms and circuits. You're basically, when you're doing quantum, you're basically sort of in the mid. You have to think about being in the middle of hardware and software. It's a bit of a little bit mindset change. So definitely go do the free stuff if you're just beginning. So
Yeah, I appreciate that. Now, do you get a sense of like how things are going to scale? Like say, okay, well, I wish I could do that, but we don't have that right now.
well, I mean, if you can come up with a circuit that needs 127 qubits, you can go to IBM and you can pay them. I think you might have better results going to one of their competitors at the moment, just because of the their coherence issues and stuff. IBM's major problem has to do with the topology they use for qubit interconnection. And one of the issues everybody ran into in the last lab dealing with the Eagle processor is you have to be really sensitive to what your circuit depth is. So when you're on an IBM and you want two qubits to talk to each other, if they're not actually literally connected together, the program will insert a whole bunch of swap gates to get the quantum state from where you're at to where it needs to be, and then so the way to optimize that is to pay attention to what the double hex grid of interconnects looks like, so you can put the qubits that need to talk to each other close to each other. And so again, you got to keep the circuit depth low. Otherwise, you very, you can, it doesn't sound like their Eagle has got better coherence times than their other machines at the moment. So if your circuit depth goes too long, you're just out there in noise land. All the qubits have broken down. The other thing that was a big push was dynamic programming, which is fascinating. And they did demonstrate a way where you can basically by using the dynamic programming reuse qubits and reuse fewer qubits, and that winds up keeping your circuit depth small. So you don't have, because you're reusing the same qubit, you're not worrying about swapping states, up and down the hex grid. So that part was pretty cool. But yeah, they're gonna need to come up with some solutions to some major problems. But it sure was fun being able to work in that environment in a community where you could trade ideas and stuff.
Yeah, I appreciate all that. I mean, what comes to mind is for those that want to use quantum computing, it's just going to be technical like this, especially when I talk, because, I'll be in different notebooks and trying to compare to, classical learning and try to find equivalence between the two. But as it is with like AWS and like facial recognition packages, so like you go on and, a lot of it's just done. So it's not quite as technical. So hang in there. But I would say you definitely have a leg up if you get super technical with quantum, and you're the point of like building circuits and not only just building them in Qiskit, but then moving it into different, say for instance, like a penny lane application. I do image analysis kind of stuff. So the time will come, if that's not your thing right now, to use quantum, because CPUs, GPUs, and QPUs will be a main thing. And a lot of it, especially if you use something like a pay-for service like Amazon or Brickhat, it will get less technical as you see it on the screen, I believe, in the coming years. With that being said, anybody else with IBM or IonQ? So this kind of, and exactly what you said, Ron, like from the IBM stuff into IonQ, is the IBM uses gate-based superconducting qubit, which is the theoretically most powerful. So Google is similar. So Google had quantum supremacy with it. And it's kind of interesting because with all this, dynamic programming and the things that IBM's doing to work with their faulty quantum computers, what part of that will make it to ion traps such as, IonQ? So if you look in literature and you want to find good finding, like the end result, okay, so you want to find like they had a polymer analysis, application in Nature using IonQ, ion trap technologies. And they said their results were decent, but they're still battling, noise from the quantum computer. So, and looking at these in specific, and anybody else, IBM or IonQ, either questions or if you have something to add with it? And I would say just, it seems like it's going out there as a leader. And again, if you look at their financial reports in coming years, the qubit counts aren't that high. So right now they just announced like 20 something qubits on AWS Brickhat. So it's not that the quantum, many people expect, if you read headlines, is not what is occurring in literature, because a lot of it's either ion trap technology or quantum simulators. Now, leading into the next two, Caltech and MIT. So Caltech, if you know John Preskill or the late Richard Feynman, has a tradition in quantum computing, quantum physics. And in fact, back in the day, quantum computing was not done on a computer. It was done on your paper, like you would write, and somebody says, oh, I'm doing quantum computing on my notebook, because they didn't have the hardware that, we have noisy quantum computers today. So they have a partnership with AWS, this hub. I believe it's Pasadena based solely. And then also, if Caltech is right up there as among other leaders in universities. Same thing with MIT. So this HHL algorithm stands for people's last names at MIT. So you have Seth Lloyd, you have Aram Haro, and then I don't know who the other H is, but basically they're working on quantum algorithms. You also have Peter Shor of MIT. So Peter is known for Shor's algorithm, which in theory, if we had an awesome quantum computer to run, then you could break any type of encryption across, current encryption standards with it. They also have a Torch Quantum, which is basically PyTorch with quantum. And then, so PyTorch is the classical version and Torch Quantum is quantum. And also quantum engineering. So this has come up in other, other groups too. It's going to be it's basically the application of quantum computing across disciplines. So, there's a lot going on there. So anybody have anything as far as Caltech and MIT? So Caltech is in Pasadena, California. MIT is in Boston, Massachusetts. So go ahead, Ron.
Well, it's interesting that you brought up Caltech there as we speak in the middle of their spring or summer quantum workshop. There's a whole series of presentations going on. And I watched a couple this morning, and there's some fascinating new developments going on in materials. And one of them was on the neutral atom stuff. That's getting some traction. So there could be some new breakthroughs any day now.
Yeah, I appreciate you bringing that up because it's, so this weekend was the big news for IBM. They say in 10 years, we'll have 100,000 qubits. Now they're also partnering with, so Ron's out in Chicagoland, University of Chicago, Fermilab, and I think one or two other, big key name institutes with it all. And it's starting to funnel down, right? Because we have IonQ announcing the, manufacturing facility early next year. Now we have IBM giving a more definite qubit count, a little bit, say 20, kind of 3 years maybe off of what some people thought was 1 million qubits by the end of this decade. So it's interesting because there's articles out there that says neither of those two, that it's going to be quantum simulators. So quantum mechanics running on CPUs and GPUs. So my guess is it's going to be a mix. But that kind of crossed my path as seeing the collaboration with different parts of the country with IBM, maybe a recognition that the technology is just not ready. And I think a lot of things have been alluding to that with gate-based superconducting qubit. And then, going back to Google, they announced quantum supremacy October 2019. And then since then, they haven't really announced any new hardware. They've just been trying to make it better, adding quantum sensors to it, basically trying to get quantum memory to assist with the noisiness of the quantum computer. So I don't know, that's how it feels like to me is things are definitely starting to narrow down as far as which of these technologies will be used in applications, even within the next year. Anybody else? So Caltech or MIT? And then feel free, if you don't want to come on, or if you don't want to unmute, feel free to put it in the chat as well. Anything's fine because we all start off with general news. And then once you start getting into the papers and doing your own application, it just gets more technical. So anything, kind of more general is fine too. Now, the last couple, actually, let's just do Quantinuum and Microsoft. So Quantinuum is a spinoff of Honeywell, and Honeywell is a Fortune, I think, 100 company, huge company. And there's some logistics behind that, but basically it's a separate company. It's associated with Honeywell. And their news tends to be very technical. So they share the paper, they provide the news, say for instance, if they have like a quantum volume of 8,000 and now it's closer to like 80,000. So basically it's a measurement of qubits and error. And then also, now you have this 32 qubit GHZ circuit run on it. So, Ron might be able to comment on that, but that's a challenging thing for a quantum computer to do, is fully entangle a circuit for 32 qubits. So, that's right out there as far as the stuff of thing like IonQ is claiming with their ion trap technology. And then, so Microsoft, maybe a little bit quieter, at least I don't get it in all my alerts, topological qubits. And then so you have Majorana fermions, and then you also have they're getting DARPA 5-year funding. Like I said, some free credits coming up. So basically, you do have to give them your credit card up front, I believe, but you have some free credits to use something like an ion trap computer. So anything with that? Any questions or any comments with Quantinuum or Microsoft in regards to this? So this is quantum machine learning in healthcare. And it's definitely been interesting because like when I first got into this, so this is 2021, and I would read papers, and I read a Microsoft paper that had to do with a catalyst, and it's basically turning CO2 or carbon dioxide into methanol and water. Now, in theory, that's not that complex of a task to do because it's not a biopolymer. It doesn't have huge molecular weight. And anyways, at the end of the paper, they said that we needed 1,000 qubit topological quantum computer. So a lot of things there, all of this I'm talking about is just like the general press stuff. So who knows if they're working on anything else, those types of things. But just I would say a little bit quieter, maybe with a technology. If it works, it's kind of awesome kind of thing. But we just haven't seen, that rapid development, or at least announcements from it too. And then also Xanadu. So Xanadu has PennyLane. So Xanadu is photonics quantum computing. And, I think it's June 22, they announced they had quantum supremacy using their technology. PennyLane is huge in literature. So that seems to be the default. It came out the first out of all the quantum machine learning. Qiskit came out prior to it, but QML came out first in Xanadu PennyLane. And I'm using a simulator now. So they have one of theirs. So they have default.qubit, default.mix. If you're running in C++ to make it faster, you also have the lightning.gpu, which is in collaboration with NVIDIA. And then you also have lightning.qpu. And they won't run unless the code's in C++. I found out the hard way. So it's an interesting thing because you have all of these going on, and any could break too. And there's neutral atom, there's silicon spin. We've talked about NVIDIA, so their GPU technologies, either as the simulator or helping a quantum computer. We could still have that hockey player taking a slap shot kind of feel. That's what it was first described to me, back in 21. But over the course of this, year and a half, that isn't the case, right? It's more of a gradual progression. So any other questions or comments? So Quantinuum, Microsoft, or Xanadu. So it's definitely some interesting stuff to get into. And feel free to put anything into the chat. And it'd be awesome to kind of get like a sense as far as like, do people want to get heavy into programming it? You just want to use it for your specific application to get quantum advantage. There's much to talk about in both of those. So you can get quantum advantage with QML these days. I've experienced it. So Xanadu, so Maria Schuld from Xanadu, she said the same thing too. It's a QHack earlier this year. It's a specific thing. Like, so does that part of the code take advantage of quantum mechanics better than if you just left it alone classically? And keep in mind, it's going to be slower if you do it on a simulator at this point. And I see people from definitely different backgrounds, maybe more classical on the supercomputer end of things, and then maybe more academic here as well. I'd love to hear from you. So if you could either, unmute and or you can come on as well. And I guess I might have left out a group as just like, maybe you don't know, maybe you don't know where quantum is going and you want to get a better idea. I would say in the near term, it's definitely going to be on simulators, maybe some ion trap hardware. for doing tasks that we know just is better to do on using quantum mechanics. So, and I could talk ad nauseum about image analysis and which parts of the code, like, so your deep learning, your convolutional neural net, there's been a couple attempts to insert quantum code there, like as the IBM did it, Penny did it. I saw another brain tumor paper that did it too, but it's actually in that process of sliding a window over an image, basically convolutional. And then transfer learning, more towards classification end. So this is, the step right before final classification. So you have a number of qubits, and then those gates, and then it gets turned into, it gets cut in half from the number of qubits that you have. So this is all according to reading literature and experimenting with it too. Anybody that we haven't heard from? So Michael or Joe or Gochin?
Hello, my name is Gökçen. I'm a total beginner. I'm very much in the beginning of the path here, and it was really interesting. Thank you all for sharing all your insights.
Yeah, I mean, that's totally fine. It's just, just don't give up with quantum, and that's the biggest thing. And definitely hop on to maybe IBM Qiskit. You can find a fair number of tutorials on there. You can find also, if you have programming experience, tutorials on PennyLane. So that's, it's Xanadu PennyLane. And, some of it's, if you know classical, you can do this. Other things, it's that specific quantum circuit, like defining it and then, setting up the layers, that kind of stuff. You'll probably want to know at least, they're called gates and circuits. Yeah,
Great,
and then
thank you.
Yeah, anything else?
No, I was just gonna say, just to kind of briefly introduce myself. I'm a data scientist with some background in mathematics and statistics. It seems like a interesting field, and I'm kind of, as I said, I'm kind of beginning to build some knowledge on that. But this was very helpful to have some beginning points. Thank you very much again.
Yeah, you're welcome. And there's definitely a lot of analogies between the two. So classical actually is needed to do quantum mechanics. So especially in the last step, it's called measuring it. So at the last step of the quantum circuit, it turns into a bit. So it's a 0 or a 1. And everything before that, when it started being embedded for quantum, was some different quantum mechanical form of rotations and entanglement and those types of things. So for me, it doesn't seem that hard anymore. But I remember when I first started, just the words, right, like superpositioning, entanglement, interference, these types of things. So. But the time won't be that long, I don't believe, as far as not having to know everything technically about quantum and get quantum advantage, because it's just like, oh, okay, like you use a ResNet 18 for classical, we'll use a Q ResNet 32 for quantum. Some part will be baked in with quantum and you won't even have to touch it. So, Ron, go ahead.
Yeah, I was just going to say, if you have interest in learning quantum computing or quantum algorithm building, get started now. I mean, even though the hardware out there is noisy and limited, especially if you want to stay on the free tier, you need to learn it. You don't want to wait until they become mainstream and the demand is up there, because you do have to think differently when programming a quantum computer. So get out there to just Google IBM quantum experience, get over there and play with Qiskit, play with their composer, and go back and watch all of Kevin's recordings for the last several months. He's got all sorts of places where you can go and do free tutorials and stuff. Do as much as you can. Because like I said, at some point there's going to be a demand, and there is one group of people that'll say, well, you could just wait until quantum computers become like GPUs. Nobody really cares about what goes on in the GPU anymore. There's a front end library. You know, NVIDIA's got CUDA, and let CUDA just worry about all the details. There may be something like that in the future, but again, building quantum algorithms, I think, is where the work is going to be. And you need to have the quantum basics, understanding superposition, understanding entanglement, and understanding how to get quantum to render its quantum advantage. And even if, I mean, it could be sometime before we have the hardware, but if you're interested in it, learn that stuff now, because I don't see that stuff changing that much. But the thing that will change will be the accessibility, the reliability, the precision of the hardware as things go along. Also, I wanted to mention that as part of my agreement or my entry into the Womanarium summer school is I have to, after that school, I have to commit to training 5 young people in quantum, and 3 of them have to be women. So
How young do they need to be?
yeah, I mean, I'm not complaining or anything, but I have no idea how that, you know, I'm hoping they're going to provide materials that I can use, and I don't know all the details. You know, I'm hoping that if I do that, I mean, I'm more than willing to, if I get to that point, is to train people. I'm more than willing to train more than 5, but that's my requirement. I've taught Python at a community college in a CE, which means non-accredited format, community education format. So I'm kind of looking forward to that. I enjoy teaching people, so that'll be after July sometime. So there's a lot of people out there making things happen, so there's no excuse not to find some free training.
Yeah, I mean, hopefully that helped everybody. And Ron's right, like, you know, in order to get the very best performance, you know, you're either going to have to pay somebody, or, you know, even better, that you're the expert and you know how to fine tune this quantum neural network in the future. So Joe put in the chat, so he's a ZOS programmer with IBM and work in QA mobile testing as well. And I would say, Joe, is just like, it's not replacing classical. I think in most applications it's just going to be to get that bump. So I've heard of like, what would these be, like a data center where they use smaller qubit, like 5 or 7 qubit quantum accelerators. I don't know, probably simulators, I'm not quite sure, to assist the current workload. So I think those are the immediate gains, is basically, okay, this is not possible to do classically. It's taking too long to do classically. Then how can we either use, you know, quantum cloud like Qiskit or something like that, or do something, well, yeah, mostly cloud in the next couple of years. That it's, you know, think of it that way, like it's the whole CPU, and I know you're using GPUs in most, or I believe in many supercomputer applications. So it's that whole thing. So definitely, I mean, I might do another one of these with definitely like a Terra Quantum and NVIDIA, kind of feature them a little bit more, because NVIDIA is just, many of the things like their quantum simulators, they're saying out to thousands of qubits. I'm not sure how fast it'll be, but it's called a NVIDIA Tensor Network GPU quantum simulator is the phrase that they put on that. And then they already have something that's helping out PennyLanes with it. So like I said, I just had like, I'm going to be publishing either tonight or tomorrow on LinkedIn, and, you know, it's, the run times are too long, you know, like 240 minutes compared to 40 minutes for the classical counterparts. Although one of mine is better than the classical. It uses a similar type of framework as opposed to a different type of transfer learning. But yeah, it all, you know, it's the type of thing, like determining quantum advantage is hard, right? Because number one, you want apples to apples, but you can't always get it. And number two, the quantum or the classical hardware is going to be improving too. I mean, same thing with GPUs too. So I've seen in some papers only go after potential exponential speed ups in quantum, because you're going to have this type of thing, this back and forth. But to do applications, you kind of have to work through some stuff and then just say, okay, well, quantum advantage, is proposed for this, but, for this specific model, and you have to figure out, is it due to some other setting or is it due to, those types of things. So, but yeah, I think it's, they said like by the end of this year, there'd be something like 70 or 80% of all classical HPCs will have some aspect of quantum computing to it. So it's not going to be in the form that you think it is. Like, I don't think like even Quantinuum's 32 qubit, that recent news that they had is probably going to be more like these smaller quantum simulators, those types of things. And I would, if you want to learn more on this, I would definitely look at resources like QHack. So it's all one word, the letter Q, then hack, because it gets super technical into it, and it's has a lot of substance to it. Anything else for that, Joe? And then, yeah, so we had Google, AWS, IBM, IonQ, Caltech, MIT, Quantinuum, Microsoft, Xanadu. That's a pretty good coverage. There's still many more companies out there that are making headwaves. So these are definitely, I would say, more of the, the back ends to it all. And, there's even in medical and health, like drug discovery, there's at least 10 companies working on applications to utilize, either simulators. We didn't mention quantum annealing, and then also real quantum hardware as well. So. And then, so it just keeps going on. We keep getting good announcements. The federal government, which we didn't talk about too much, the past 2 years, they put over $800 million into quantum information science. That's their term. And that funding goes to NSF, DOE, and NIST, are the three big ones. Now, the other big one out of NIST is called QEDC. Now, QEDC is Quantum Economic Development Consortium. And what they do is they bring together big companies so we can all figure out quantum together. So they actually have a big event coming up next month. So it's a spin-off, or it's from NIST, and this funding came from President Trump's, I think it was 2019. So anyways, the momentum keeps building up, I would say, as a whole, as a field. So it's good to keep an eye on, the general news as well. Yeah. The rules are crazy. Yeah, so there's, like Ron said, there's board games. There's all this, Quantum Leap, a second Quantum Leap, like the TV show came out, I think it was later last year. And then also a Marvel movie, Ant-Man, those types of things. So it starts to work its way into the culture. And again, like for data sensitive, like patient data and financial data and those types of things, I would have a hard time convincing investors that a NISQ era quantum computer, meaning noisy intermediate scale quantum computer, is good for this application today. But it's good to work off of. So any other questions or comments right now? Any of these companies, these QML companies? And I'm going to re-highlight basically what came up last week. So there's a company called Terra Quantum AG, and they came out with this paper, and basically they did studies on 4 different hardware companies, and then they also did their quantum simulator and Amazon's quantum simulators. And what they found is that because of quantum computers, it takes a while to boot up and this type of stuff, like to get going. They said, unless you're at 30, so 30 quantum bits, it doesn't make sense to use a real quantum computer. So on paper, the real quantum computer should be faster at low qubits, and have noise. So this 30 qubit threshold is important because, what it says is that you're going to be noise free at 30 qubits and less. So plan on designing circuits like that, like your quantum algorithms. Anything above that, they said at 40 qubits, so only 10 more, quantum computer was a lot faster. So it took 0.02% of the time than a quantum simulator. So, but it's noisy, right? So the cool thing with quantum simulators, if they get up into hundreds, what NVIDIA has been talking about, is you don't have the noise. You're not going to have the quantum speed up, like it's not going to be a real quantum computer, but you don't have the noise, and that's a huge thing. So if the runtimes are decent, using a single GPU and elevated qubits like that, you should be running a simulator. Because the noise is still way too high, I think, even for ion trap, because we're not even this is like the first of 3 stages. It's called noisy intermediate scale quantum computing. And then you have fault tolerant, and then you have error corrected. So we're not even to fault tolerant yet with the quantum hardware. But people like to see that you're running on real quantum hardware, because there's, like Ron said, like you send it to the 127 qubit and it might not even run, right? Because you can't simulate it, because we don't have simulators currently that are above, I don't know, like 40, 60 qubits, something like that. So it's a very specific thing. And if you read a lot of the literature that has the good results, it's mostly simulated. Some ion trap, they do use that, gate-based superconducting qubit, but I would say for a bigger application, something like an ion trap. Any other questions? So we haven't heard from in a little bit. So Michael or Brian? And
No, I'm
then,
just taking it in. Perhaps the title was the application to the healthcare industry. So we talked about Cleveland Clinic. We talked about some potential uses in simulation or drug discovery. Any other interesting players in that arena?
oh yeah, so Mount Sinai Hospital and Sandbox AQ, I think it was earlier 2022, they had a partnership for patient data security. So we've talked about this a little bit in more recent discussions. Is basically Sandbox AQ, Q-Secure, these types of companies, the algorithm is already set by the government. So it's called NIST and NSA, especially NIST, has these algorithms that the whole country should start implementing, and especially the quantum, especially the federal government, they're required to start having cybersecurity defense. Now, the other one is NYU Langone. So they do let's see, Fermilab. So Fermilab is working on a whole new type of MRI analysis. So this is quantum sensors, this is quantum computing, these types of things. And, basically, I think the source of the data would be from NYU Langone, which is a New York hospital in New York. So those are the big ones, those 3. So Cleveland Clinic, NYU Langone, Mount Sinai Hospital. And you're going to see more, but like in all these things, like the underpinnings have to work in order, in my opinion, because right now in ISO IEC, there's a quantum cybersecurity. I should check up on that if they passed yet. But anyways, they're further along in their routine to get ISO certification or IEC certification. It's a joint partnership for cybersecurity. Now, the next industries may be something like finance, healthcare, these types of things. So it's important because healthcare probably looks at simulators versus real hardware different, because simulators are run on CPUs and GPUs, right? So as far as the ones that make like the splash in the news, I would say, there's been 3 announcements at least for the IBM Cleveland Clinic. First, that they had a 10-year partnership, so for quantum and other AI technologies. And then the second one that they were starting to build the quantum computer, and I think it was last month or maybe the month before that it had been finished at Cleveland Clinic. So beyond that, I would say I mean, FDA looks at my stuff a lot, so it's just, it's coming to a conclusion like, okay, yeah, it would make sense to do this type of simulation for this type of data, because it's at this level. But with all things, I think it's going to have to take a closer look, as far as like the underpinnings to quantum mechanics on regular hardware.
Did you say that the FDA is looking at your materials? Are they receptive to this type of computation?
Yeah, I mean, it seems like the biggest thing is basically this is like, you have to, anytime you bring in a new type, so deep learning, right? So late 1990s, early 2000s, that, the hardware was available. We didn't get our first FDA approved algorithm until 2017 as cardiovascular. It's got a company called Arteris. So yes, they have to be aware of all this coming through, and you really have to understand what's going on quantum mechanically and what's going on classically and these types of things. But yeah, it'll take some time, for sure. I don't know if it'll be that long between like deep learning hardware was ready, like early 2000s, and then FDA approved algorithm 2017. So there's like a sliding scale, like on one end would be like, oh, okay, that's just quantum mechanics on a classical computer or a GPU. And then probably somewhere in the middle with it for simulators.
Thank you.
Yeah. So yeah, and as far as healthcare goes, it's, with quantum, trying to think, because we don't have too many of those big articles that kind of like splash down and say, okay, now we have one of these in a healthcare system. So, there's a lot of legislation behind it too, because even in New York, and I want to say Global Foundries and PsiQuantum, they had this partnership, and so politicians get involved, in helping to get quantum funding for this specific application. So the good thing behind all this industry is it started off as a government initiative, like funding. So NSF first to fund quantum computing in the early 1980s, like, over 40 years ago. And then they continued to fund. And all of these, a lot of these technologies, like IBM's technology, it's called gate-based superconducting qubit. Well, the government would always call that transmon qubits. So I know other, neutral atom and these types, a lot of it started off in the government, and maybe, it does better out in industry, right? To, get dozens of people working on the same project, and it's more open. Like the government is maybe less open. So anyways, things have moved back and forth between government and industry development with it all. And I mean, that's, for me, it always seemed like healthcare would be a great application of it. And I wasn't expecting it to just be, quantum simulators, but it sounds like those would be taking off too. So yeah, it's just, a lot of us talk about like the underpinnings behind it, because those are the things that are important to, to transfer into other agencies looking at this for regulation. So. Okay, so we do, okay, is using Q. Yeah, so, okay, so I mostly talk about medical image analysis, which is existing medical images that you're treating with quantum computing at some point. And there's different ways of doing that. So Ron brought a good point. So he says, KIP, so QIP is quantum image processing. So you can actually use quantum computing on a more fundamental basis, like reconstructing raw data into image, like it looks like an image. And there's a gentleman, his name's Salvador E. Venegas Andraca. He's spoken on this. There's a video I have up for him. And that's what he does, is he wrote a book on this, QIP. So it's more on that fundamental basis. So, and then drug discovery as well. There's another lady that talked on the Shahar Keenan of Polaris QB. And then, so she works with quantum annealing, which we haven't touched on tonight too much. But quantum annealing is basically, it's only for optimization problems. If you have 5,000 qubits, it's not the same as 5,000 qubits like IBM or Google. It's a company called D-Wave that does it. And it's gotten pretty good number of applications. They said 250 plus. Now, keep in mind, a lot of these will just be quantum proof of concept. I don't think it's going as far as trying to prove to a certain extent that you have quantum advantage. But, you know, they have have like some RNA stuff, but in all these things, like for drug discovery, there's a lot of approximation. So if you have a 3D molecule, well, even a quantum annealer at 5,000 qubits can't handle that. So you have to flatten it down into 2D. So you're looking at a 2D molecule. And then, you know, and then you're doing approximations. So your client wants something and you can give them better approximated data with quantum annealing than you can just classically. So I haven't looked into it too much as far as, you know, a specific application, but I've heard other things that you could do even with medical analysis, like feature extraction, you know, for using quantum annealing. So their website is something like D-Wave Sys, like for system at the end. And let's see, any other comments here? Anybody that we haven't heard from? So, and you could, you know, feel free to put in the chat again. So Michael or Joe, or you can come back on, Brian or Ron.
I did have one comment about something interesting for everyone in case not everyone's aware. So Google did run the simulated wormhole on their quantum hardware. That experiment was very interesting. Bunch of caveats, but that was, you know, that's like one of those newsworthy things.
You remember when that was, Brian?
I believe it was last year or this year.
Okay. Yeah, it's with all this stuff, like I don't even really read like the just headline news because it's just, I'm going to read the article anyways, or I try to read it, you know, if I can understand it. And you know, it's just different because like the Microsoft stuff, like the headlines, it'll be like this quantum catalyst. And then I had to read the paper to figure out like that quantum computer that they want to do on this. And they thought that they had everything set up, you know, 1,000 logical qubits. I don't even know if we're talking in the next several years. So yeah, it's hard to do, but like, you know, to read all of the literature that you're interested in. Yeah, so Rana brought this up. So resource management issues for quantum or for large medical entities can be, yeah. So again, like the thing with quantum annealing is it's a real quantum computer too. It has some error as well. So how does that work in with the end result that you have is my concern with that. Now, for those of you that are more in industry, so Dell and IonQ, which is Ion Trap Technologies, they have this thing called something like a 30 qubit emulator. So as far as I know, it's not a real IonQ computer, but it's emulating. So it's like a simulator. And, you know, that's based off of a hardware or a simulator that doesn't have noise, and it's on their commercial, you know, site. So I'm not sure to what extent people are getting, you know, emulated quantum mechanics results, but they kind of put it front and center on their enterprise, you know, like a more technical page. And it, like I said, it just feels like things are just narrowing down, you know, especially, you know, with the hardware side of it. I don't know. I mean, on one extreme, it could be like a lot of ion trap quantum computer, even in the next year and going through next year too. But a lot of the ones that got DARPA grants, that may signify that the hardware is not quite ready yet. Like, so that's Microsoft and others. I think it was PsiQuantum. So Yeah, so, and just keep reading, keep reading papers too, because papers are a lot more dense than mainstream news. It's just my finding with this all is, don't stop at like, what one thing says about one thing, because sometimes some of the details aren't the same as the the actual paper. So, and then get into an application too. If you're super interested, find something like a PennyLane tutorial, Qiskit tutorial, kind of perfect the whole thing. I've had to change circuits and algorithms, all this stuff. There's an IBM, one of my first one that I did, if it wasn't my first one, it took me a while, like several runs. And then finally I figured out a pattern in the quantum circuit. So then I just applied what I learned somewhere else into that. And it was like, boom, like 100% training, 100% testing accuracy. So, but you don't know. So a lot of things are still experimental. So when I talk about these things, they say this circuit should run best, like maximum entanglement, best, match to estimated probabilities. But a lot of times you just have to run it in your circuit because that might not be the limiting factor. Like if you're doing quantum machine learning and it keeps passing through it and it doesn't like that, that specific recommended circuit. So. Awesome. Any other last questions here? So we talked about Google, AWS, IBM, IonQ, Caltech, MIT, Quantinuum, Microsoft, and Xanadu. Definitely going to be players. There's others like Terra Quantum. There's NVIDIA for sure. I might feature later in a later discussion. But, the devil's in the details for sure. And as some of these forums, like if you go on Meetup, they start to transfer into something like, hybrid coding. It's not there yet. It's all Python. And basically you have to win these people over because you're coding in quantum. And if you're sure about it, right, then they start to like come closer, right? But it's not a mainstream thing yet. I would say if you take Python or coding, 9 times out of 10, unless it's mine or Anna's from Chicago or Toronto, DC, those seem to be the other ones kind of still in there that, you go with it. It's intuition. You see, funding amounts, you've seen papers, all these other kind of signs to keep developing with quantum. Awesome. Well, I appreciate everybody coming on. This has been Discussion 84, Thursday, May 25th, 2023 for QML and medical innovation. Appreciate everybody coming on. Have a good rest of your night. Have a productive rest of the week. Take care, everybody.